Hi, welcome to CS188 Section 4, and today we'll be going over the solutions to the worksheet. So in the first part, we're going to be doing some expect-to-max problems. So let's consider the zero-sum game tree below. So instead of the minimizing player, we have the chance node. So these are chance. And we also know that they select one of the three values uniformly at random. So whenever the chance has an action, there's a 1/3 probability that they choose any of the actions. So now they want us to fill in the expect-to-max value of each node. Okay, so first we start at the max and we go left and we reach the expect-to-max. So how do we compute the value? It's the sum of the probability times the value. So it's going to be 1/3 times 10 plus 1/3 times 8 plus 1/3 times 3. So if we sum them all together, 10 plus 8 plus 3, we get 18 plus 3 is 21, divide by 3, that gives us 7. Now we go to the next one. So because it's uniform random, we can sum them up and divide them by the number that we sum by. So 2 plus 15 is 17, plus 7 is 24, divided by 3 is 8. And the last one is 6 plus 5 plus 4 divided by 3. That gives us the mean of 5. And maximizer will choose the best one, which is 8. Now question 2 asks us which nodes can be pruned from the game tree above through alpha beta pruning. If no nodes can be pruned, explain why not. So first I'll just say that, okay, so in alpha beta pruning, normally for minimax, what we can see is that, okay, when we're considering one node, that maybe at some point we would never even consider this branch because the other branch was somehow better. But the problem with expect-to-max search is that the value of a chance node depends on the value of all the children beneath it. So the answer is going to be no nodes can be pruned. So an explanation is that when you're doing the chance node, that you're looking at nodes one by one, and that there could be some node in the future that could pull up your value that would make your branch seem even better. So for example, let's say I added here a 1000. Then all of a sudden, this node becomes way better, and then we decide to choose this one. But I didn't know this 1000 was coming up. The only way I could know that it was there was if I had actually visited it. So that's why we can't prune any nodes for expect-to-max search. Okay, so now let's look at 3. So this is a non-zero sum version of the game. So player A's utility is the left of, so for example, it would be this 10, and player B's utility would be the right. And agents always want to maximize their utility. So the triangle up wants to maximize the first number, and the triangle down wants to maximize the second number. So now let's fill in this non-zero sum game tree. So when we assume each player is acting optimally, we mean they're trying to maximize their utility. So we start at the player A, and then we go to, so it's A, this is B, and we go to player B. So we only need to actually look at the right values. So 1, 3, 5. So we choose the 5. So that gives 3, 5. And now we go to the middle node. So we look at only the right values, 4, 9, 8. So we take the 9, 15, 9. And then we go to the right. So we look at 5, 10, and 12. And we take the 12, which has a 4 associated with it. Now A is only going to look at the left values. So 3, 15, or 4. So A best prefers 15. And that's how we run this non-zero sum game version. Now they're going to ask us a similar question. Can any values be pruned through alpha beta? So again, the answer will be no. But let's think about why. Okay, so let's look at this above example. So I went through the left one, I got 3, 5. Then I went through and I got 15, 9. Now, if I'm going to the right tree, the only way I could prune anything and ignore any state would be if I know that player B would choose an action that would hurt player A. As in, player A would never go down this right branch. But since they have separate utilities, it's non-zero sum, there could exist something that's good for both of them. So maybe over here, there could exist something that was like 1,000, 1,000. So it's great for both players, so they would both do it. So because this is non-zero sum, we don't have any knowledge about whether this will happen or not, so we can't prune. We can't ignore any of the nodes, so we have to expand it all. So we can't do any pruning. Okay, so now we're going to do some work with utilities. So in this problem, they say consider a utility function of u of x equals 2x, and they want us to calculate the utility for varying values of x. So for a, it's pretty simple. So we do u of 3 equals 2 times 3 equals 6. So now, next we have a lottery. So the utility of the lottery is the probability times the utility of the value, which will be 3 plus 1/3 times the utility of the value, which is 6. So if we map this, this will be 2 over 3 times 6 plus 1 over 3 times 12, and that'll equal 8. Okay, so now let's say if we have utility of -2, so equals 2 times -2 equals -4. And finally, for D, we have the utility of this lottery is going to be 1/2 times 2 plus 1/2 times another lottery. So what is this lottery? Well, it's 1/2 times the utility of 4. Sorry, this should be utility right here. Plus 1/2 times the utility of 6. So if you plug in the utility for this equation, then what you'll end up getting is you'll end up getting 7. Okay, now they're asking us to consider a different utility function, this time x squared. And they're going to ask us the same questions over them. So for the first one, the utility is just going to be u of 3, which is 3 squared equals 9. And for the next one, the utility of the lottery will be 2 over 3 times the utility of 3, which is 3 squared, plus 1 over 3 times the utility of 6, which is 6 squared, and that equals 18. Now we want the utility of -2, so that'll be -2 squared, which equals 4. And now we have this lottery within a lottery, so we have 1/2 times the utility, which is going to be 2 squared, plus 1/2, and then we have the lottery, which is 1/2 times 4 squared, plus 1/2 times 6 squared. If we plug and chug, we get 15. Okay, so hopefully you're comfortable now with utilities. Okay, now we're moving on to a problem with Markov decision processes. So our Markov decision process is given by this diagram right here. And let's read through it. So the rewards on the above are indicated by the number on the transition. So for example, going from state B to A gives a reward of 10. So B to A gives 10. But if you're in A and you go back to A, it's 0. So that's this arc. And some transitions are not allowed from A to B. So there's no arrow from A to B, so that means we can't do that. Okay, so what they're going to ask us is a bunch of questions about what we should do for each state given different discount factors. So, apologies, this should read gamma. Okay. So, let's see, write down the optimal action if the discount factor is gamma equals 1. So if you remember for the overview beforehand, gamma equals 1 means we care about all actions, all rewards equally. We don't care what time we get them at. So for gamma equals 1, this means there's no decay. Basically, all rewards are the same. So if we look at this board, what we can see is basically everything gives 0 except this 10 and this 1. So since we're playing for all time, we're playing from t equals 0 to infinity, what we would want is we'd want to be in state F and just keep getting this 1 forever. Just 1 plus 1 plus 1 all the way to infinity. So because there's no decay, that's what we want to do. So let's say the answer is going to be for states B through F, you want to move towards F. And once you're in F, you want to stay there. Now for state A, you have no option. You have to stay there, since that's the only arrow. Okay, so now let's move on to number 2. So they want us to say write down the optimal action given that gamma equals 0.01. So gamma and gamma. So I write gamma in 2 different ways. This one and this one, they're the same thing. Okay, so now we need to think back and how do we calculate the reward? So the reward is the sum from t equals 0 to infinity of gamma to the t and the reward that you get. So let's go one by one, and what we can tell just by looking at this is we have 2 choices. We can either go to F and stay there forever, or we would go from B to A. It doesn't make sense to go and stay anywhere else because all those rewards give 0. So first, let's start at F. So at F, we can decide to stay there, and if we do, then we get the sum of rewards, discount rewards, and it will be gamma to the t times our reward, which is 1. So it ends up being 1 over 1 minus gamma, which equals 100 over 99. So that's if you go right. Now, what happens if you go left? So if you go left, we can count how many discounts, how discounted this 10 will be when we finally get there. So if we do that, it'll be gamma to the 0. So 0, and then 1, and then 2, and then 3, and then 4. So it's going to be a discount of gamma to the 4 times the reward we get, which is 10. So that equals 1 over 100 to the 4 times 10. And that's for left. So we would actually choose to stay at F. Now let's work left. So we look at E, and if we go right, what it would cost is it would be a discount of gamma times the discount reward we would actually get at F, which we already calculated as 1 over 1 minus gamma. So that would equal 1 over 100 times 100 over 99. And that's for going to the right. Now, if we want to consider going to the left, it would be the exact same as we calculated before. So if we're at E, it'll be 0, then 1, then 2, then 3. So there would be gamma to the 3 times 10, so equals 1 over 100 q times 10. And that equals 10 to the 1 over 10 to the 5th. So that's actually smaller, so we'd actually decide to go to the right. Now let's keep going. So for D, it's going to be the same calculation, so it'll be gamma squared though, because we're one farther away, times 1 over 1 minus gamma. So that equals 1 over 100 squared times 100 over 99. So that's 1 over 100 times 99. And that's if we go to the right. But if we go to the left, it'll be gamma squared times 10, which will actually be bigger if we just look at these two. So we'll actually decide to go left at that point. So we could continue this, but it seems we found the flipping point. So if we go and calculate C, we would also find that we would go to the left, and B, we would also find that we would go to the left, and for A, we have no choice. We have to stay at A. So I guess that's also going to the left. So now let's look at number 3, which says for each state, does the optimal action depend on gamma? If so, find the value at gamma at which the action changes. So we can tell immediately that for action A, it doesn't matter, because there's only one action. But now, let's look at B, and let's look at the calculation that we did in 2. So we had a choice. We could either get the reward of 10, or we would go to the right and try to get the reward from staying in F. And that was gamma to the 4th times the discounted reward, which is gamma to the t times 1, because it's 1 right here. So that equals gamma to the 4th times 1 over 1 minus gamma. So depending on gamma, if the right side is bigger, then we'll go to the right, otherwise we'll go to the left. So let's do this for C. So for C, if we want to get the reward from the 10, it would take 1 step. And now we have to compare that with gamma cubed times 1 over 1 minus gamma. And then for D, we're gamma squared away. And we have to compare that with, now we're getting closer, so the discount's having less of a factor for F. And then we do that for E. So going to the left is even further, getting closer. And for F, we're the furthest away from the B value. Well, it's actually just 1 over 1 minus gamma right there. So depending on the value of gamma, that'll decide whether the question mark is a greater than or a less than.